So in this little video, I will briefly be discussing my recent publication with Professor Kevin Bedell in the New Journal of Physics, entitled The Necessary and Sufficient Conditions for the Validity of Luttinger's Theorem. So let's briefly first discuss what Luttinger's theorem is. Luttinger's theorem is a very simple idea that basically says the volume of the Fermi surface for some general interacting system is equal to the many-body particle density. Now, we can go into the details of the implications of Luttinger's theorem in the paper, but what I want you to take away from this brief discussion is that Luttinger's theorem is a non-perturbative theorem that describes collective behavior beyond some cutoff near the Fermi momentum. So whereas Landau-Fermi liquid theory is only well defined near the Fermi surface itself, if a system in general obeys Luttinger's theorem, this tells us that the interacting system has the same fermionic degrees of freedom as the non-interacting system. So it tells us something about degrees of freedom deep within the Fermi surface. Now, Landau-Fermi liquid theory trivially obeys Luttinger's theorem, but the question of when and where Luttinger's theorem is obeyed in a generic fermionic system is still up for debate. We've known since the 90s that Luttinger's theorem is obeyed in a 1D Luttinger liquid, but whether or not it is obeyed for a generic mod insulator or the pseudo-gap phase of the cuprates is still up for debate. So what we want to ask in this short presentation and in this paper is what are the necessary and sufficient conditions a many-body fermionic system must obey if Luttinger's theorem is to be preserved. So to do this, we want a more robust definition of the Fermi surface. And so therefore we want to invoke the effective action of the many-body system known as the Canov-Bain functional. Now, from this, we basically have shown in the paper that we can derive some anomalous phase of the generating functional of the many-body system. This is given as some winding number in phase space. Now, you'll notice that the winding number will be non-zero for some Fermi surface that is zeros of the inverse Green's function, but it will also be non-zero for Luttinger surfaces, that is zeros of the Green's function itself. By invoking the form of the Atiyah-Singer index theorem, we have shown in the paper that both Luttinger and Fermi surfaces can be mutually defined as lower dimensional manifolds of gapless chiral excitations. Due to their similarities to topologically non-trivial entities in helium-3 known as boujums, we have called these generalized Fermi surfaces SNOCs, after Lewis Carroll's famous poem. Now, we want to basically understand what are the necessary and sufficient conditions for the validity of Luttinger's theorem and connecting these to the existence of a SNOC, or generalized Fermi surface. We have shown this in detail in the paper, and we have basically shown that Luttinger's theorem only depends upon the relation between the real and imaginary parts of the self-energy. What we have shown is that if the imaginary part of the self-energy goes as omega to the alpha, the real part will go as omega for alpha larger than 1, obeying Luttinger's theorem, while it will go as omega to the alpha for alpha smaller than 1, violating Luttinger's theorem. The latter case actually corresponding to the gapped pseudo-gapped cases. Now we can bring this all together, and we have shown that Luttinger's theorem is only obeyed for systems that lack a gap or pseudo-gap. Only those systems with a non-zero winding number n, that is systems with SNOCs, support gapless excitations. And therefore we have shown that the sole necessary and sufficient condition for the validity of Luttinger's theorem is the existence of a SNOC. So this is a very powerful statement in the sense that if the system in question has a Luttinger surface, it can still obey Luttinger's theorem. In the paper, we actually derive a single equation that tells you if you get your self-energy from RPES or some DMFT calculation, if your system in question obeys Luttinger's theorem. Hence, even if your system does not have a well-defined Landau quasi-particle, it can still have the same basic number of fermionic degrees of freedom as a non-interacting system. So to see more details, I invite you to read our paper, and I thank you for watching this short video, and I hope you have a nice day.